So the delineation, the rule, is that if the common ratio, oh, my Apple Pencil stopped working. If the common ratio R is less than 1 and greater than 0, the infinite geometric series converges. If R is greater than 1, then it diverges and we cannot find the sum. So a sequence that converges, if you think about it graphically, it's like the points are getting closer and closer to 0. It converges to a single value. We can actually find the area under the curve. That's the sum of all the parts. But if it goes in the other direction and my points keep getting bigger and bigger, I can't find this infinite area because it keeps getting bigger as it goes to the right. Those are some calculus thoughts for you, okay? You can just memorize. If my common ratio is between 0 and 1, I know that it converges. If it's greater than 1, it diverges, okay? So, an infinite sum in the format of a sub 1 plus a sub 1 times r, a sub 1 r squared. So this is the geometric sequence.
Wait, why is it and? Shouldn't it be geometric?
Oh, I think it wants infinite. I hate these fill in the blanks because I never remember what they're supposed to be. It's called an infinite geometric sequence. Is there? Yeah, there's a third line over there. So infinite geometric sequence. And the reason is that the sum goes from 1 to infinity and it never ends. Okay? So as we're thinking about this, we continue adding values forever and ever and ever. If the sequence converges, then we can find the sum. If the sequence diverges, then we cannot. If the infinite sum can be found, it converges. And if the infinite sum cannot be found, then the series diverges. So we're not going to put down no solution. We're going to say that it converges or it diverges. And I don't know why there's not a spot for it, but there is a formula for an infinite sum. The formula for the infinite sum, it's the hold on. So the sum to infinity is the first term divided by 1 minus r, the common ratio. Okay, so let's look at the sum. And I'm going to add one thing. The common ratio, we're actually looking at the absolute value of the common ratio. It's okay if it's negative. It's just that the sequence oscillates. It'll alternate positive, negative, positive, negative, positive, negative. You're going to see this in our first example. So in our first example, this is an infinite sum of a geometric sequence. So I know that my first term is 7, and my ratio is negative 3.5 divided by 7, which equals negative 1/2. That means that my geometric sequence, so when I find my nth term formula, it's going to be my first term, 7, times my common ratio, negative 1/2, raised to the power of n minus 1. So first of all, there's my nth term formula, okay? Now, if I want to find my infinite sum is my first term divided by 1 minus r. And if r is negative, remember that you're plugging in that negative, so it's going to switch to addition. So I've got 7 over 1 plus 1/2. 7 divided by 3 over 2. So I'm going to have 14/3. In a lot of ways, like, this is the most confusing concept, but it's also the easiest formula.
Sorry, this was 7 times -1 to the n minus 1.
7, so this is my nth term
Okay.
formula. It technically didn't ask me for that, so that's kind of extra, but like that's the formula that created that series. I should say that's the formula that created that sequence. The sequence is the, or no, yeah, series was the right word. The sequence is the list of numbers, the series is the sum. So that's the formula we use to create the series where it's all being added in a row. In order to calculate the sum, I was using that formula for an infinite series. Okay, let's try the next one. So last one we have here. Our first term is 9. Our common ratio, 12 divided by 9, or 4/3. We always want to have an exact value. You start rounding this and you put something like 1.3 or whatever, you are going to get wrong values. So fractions are your friend here. So that means that the nth term formula is going to be our first term times r, 4/3 to the n minus 1. I could ask you, what's the 25th term? And you could calculate it for me if we wanted. And then our summation formula, our infinite sum, is not possible. The r is greater than 1. 4/3 is greater than 1. Our series diverges. It was not. So negative 1/2, we're looking at the absolute value. So 1/2 is less than 1. 4/3 is greater than 1. So that's why you can't just say it's a fraction. You're comparing if it's greater than or less than 1. It could be a fraction, it could be a decimal, it could be a whole number. If it's less, well, it can't be a whole number less than 1. But if it's between 0 and 1, it converges. And if it is greater than 1, it diverges. That's all I got.
You wouldn't include the 1 minus part. We don't include that.
You are not checking the formula. You're checking the r value.
Okay.
Let me repeat that. You are not checking the formula. You are checking the r value, right? So on this one, my r was negative 1/2, so that one converges. The other one, it's 4/3 is bigger than 1, so it diverges.
Can we write that on the post-it?
Sure. And if you were looking at like the formula sheet included that, but look how it said. Absolute value of r is less than 1. So instead of writing it out in a big old sentence, if you can wrap your head around that, it gives you the same information and takes up less space. I would definitely, so like this formula sheet kind of has all the information, but I would make some choices about what I want to write down, how I know it's arithmetic or geometric, how much do I want to include, what do I need. For example, I might only put the nth term and the sum. I probably wouldn't put a formula for common difference. I would just remember that. And for geometric, I probably wouldn't write a formula for common ratio. I would just try to remember that. Other questions? Okay.